All right, now we're going to take a look at some pretty basic rational functions. Before break, we looked at reciprocal functions, which were quite simple, where you just have a function with a constant term divided by x, for example. And of course, we looked at it after transformations, translating up and down and left and right, and what that would look like, stretching, reflecting, etc. Now we're going to look at where we have polynomials, and in this case specifically, a linear over a linear. Those could be as simple as just x, for example, over 2x plus 1, but it could have more going on. So where you have variables in the numerator and the denominator. And standard level, you will never have quadratics or anything like that in a rational function. Higher level, in the next days, we will take this a little bit further. Some key features, some of these are new, some of them are exactly what is always true. For example, intercepts are always the same. You have a y-intercept when x equals 0 because it's on the y-axis, and you have x-intercept where y equals 0. And of course, because it's a function, you can't have more than one y-intercept. Then you have asymptotes. These asymptotes are also similar in the way that you've seen them before. It's where, in some sense, certain behavior can't happen, where we're approaching a line as we move towards infinity in a certain direction. So you could find these just naturally thinking of domain and range, but here's a quick little trick for those if you'd like to use them. The vertical asymptote, of course, is where the denominator equals 0. Where can you not divide by 0? It's when x is equal to negative d over c. If you were to set the denominator here equal to 0 and solve, you would get this. And make sure, of course, that you use the equation x equals, and then for the horizontal asymptote, y equals, otherwise it's meaningless. And the horizontal asymptote is when the denominator of the inverse would be 0, of course. So if you were to rearrange x and y, where you're going to get problems. I'm not going to go over how you find the inverses here because we've done that. But you can look at it or ask me if you would like to see how you would find the inverse of these, or just work through some rather simple algebraic manipulation. So feel free to note these or just work through them with your understanding of domain and range. Here are a couple examples. The first example, when we graph these, we're going to look at those key features of intercepts and asymptotes, and then remember that rational functions, like reciprocal functions, are either going to have branches in the first and third quadrant or in the second and fourth quadrant. So the x-intercept is where y equals 0, and the y-intercept, which is even easier here, is where x equals 0. So when x equals 0, we get 0, negative 1 over 4. And you can put this on negative 1 over 4. And then we could solve this as well when the y-intercept equals 0. Of course, when this equals 0, 0 divided by anything is going to equal 0. So when x equals 1, we'll get that the numerator is 0. Even if this is 4, it doesn't matter. So when x is 1. Okay. Now we're going to look at some asymptotes, the horizontal asymptote and the vertical asymptote. The vertical asymptote is where we have a domain issue. So where does the denominator equal 0? We will see that this is equal to negative d over c, because as I subtract 4 and divide by 2, I get negative 2 equals x. Of course, you see that this is a full equation with an equal sign. So negative d divided by c. And asymptotes are usually shown by these dotted lines. Negative 2. Okay, they go on forever and ever. So I can already see this forming, and I can imagine how that's going to look. And the horizontal asymptote, instead of finding the inverse, I'm just going to say, remember that that's equal to a over c. Okay, so a is 1. Do be careful if you have it in a different form that you're looking at coefficients or constants and not just the first thing you see or whatever else. So c is equal to 2, 1 over 2. So you can often see that here, 1 over 2. There's the y equals 1 over 2. So there's my horizontal asymptote. Probably not the greatest scale for this, but also not a huge problem. So if I were to sketch this, we know we're going to keep approaching that. You could use more values if you'd like. This is going to have a similar shape here. Maybe I look right here and find out what that is at -3, -3, -4, -6, plus 4 is -2 at -2, or at +2 there. And then we can sketch more here. Okay, the most important things to show on here are going to be your intercepts and your asymptotes, and that you have the branches in the right shape and in the right quadrants. Everything else is just a sketch. If you did need to draw it, you'd need to use a few more points. Okay, one more example. You'll see that this is not yet in the form that we're given here. You have a few different options. You could just look at this as if you had this as a rational function where a equals 1, b equals 0, c equals -1, and d equals 2. Again, writing it out and thinking of those identities here, 1x plus 0, -1x plus 2. And then transforming it 3 units in the positive, or translating it 3 units in the positive y direction. Or you could write this as a singular fraction with a linear over a linear, which is what I'm going to do in this case. Either way is completely fine. I just don't want to sketch two things and think through it. So in order to make this 3 a fraction that I can combine, I will need to multiply by 1. This is just a special one. 2 minus x over 2 minus x is 1. Anything divided by itself is 1. So if I were to multiply this out, now I have 2 minus x in both denominators, 6 minus 3x. Because the denominators are the same, I can write them as one fraction and add the numerators. So I have 6, and then positive x minus 3x is minus 2x. You could leave it like this. I'm just going to write it in the same form. So negative 2x plus 6 over negative x plus 2. Okay, you can't just cancel out things you see in each term. That doesn't quite work that way. You could factor if possible. Like I could take out this negative in both. Doesn't particularly matter. I could call this 2x minus 6 over x minus 2. I'm just going to leave it like this for now. Might be the more proper way of writing it without a leading negative, but it's fine. This is probably the better way. But for seeing these values, this is quite nice. So now I have a linear divided by a linear, and I can think through those intercepts and asymptotes that I want to sketch. So y-intercept is where x equals 0. The y-intercept, so 0, 6 over 2 equals 3. So I'll put that here. And the x-intercept is where the whole function equals 0. So if this numerator is 0, then the whole thing will be 0. So if I solve that, here we go. There's my function there. That's going to be at positive 3, because negative 6 plus 6. Okay, and I'll just check those. And that's right. Good. And now we have the vertical asymptote is where the denominator equals 0. And the vertical asymptote is where it crosses the x-axis. So x equals negative d over c. So negative 2 over negative 1 at 2. So x equals 2. We can't kind of go there. And then the horizontal asymptote is going to be at y equals a over c. And a nice little trick you could do is just do this. Y equals negative 2 over negative 1 also. Y equals 2. Okay, and now you can sketch the rest of your shape here. Your 2 branches going to be in the reflective quadrants. And there would be our function. And you could take a look and think through what this would be, and then translating it as well and see if you get the same thing.